Hello everyone, welcome to our channel OnlyPhysics JEE Grad. So today we'll be discussing JEE Advanced PYQs, JEE Advanced PYQs from the chapter KTG. Okay, this will be the first video from this chapter, Kinetic Theory of Gases, and the topics we'll be discussing are ideal gas and speed of molecules, RMS, average speed, etc. etc. Okay, there will be 25 questions in this video we'll be discussing. So let's start with our first question. We have the temperature of an open room of volume this. Okay, so room is open and volume is this. The increase in temperature is like this due to sunshine. The atmospheric pressure in the rooms remains this. Perfect. If the Ni and Nf are the number of molecules before and after the heating. Okay, so perfect. So what is happening is we are taking our system as this container. So or room. Okay, so this is our room and this is our system itself. Okay, so what will happen due to heat, temperature is rising, right? Because yeah, in the question it is given that temperature is rising, some molecules will leave the room. Okay, so we'll discussing only the system. So we have only the system, right? Perfect. So what we are going to do is we'll write PV equals to nRT. So PV equals to nRT, right? So volume of the container is same and the pressure in the rooms remains the same. So this is same. So clearly we have this is constant equals to, we can write it as number of molecules, R is constant, and A Avogadro number and into T. So we will have simply N to T is constant, right? So we can simply write N1 by N2 will be equal to T2 by T1, inversely proportional. This relation is inversely proportional, right? So N is inversely proportional to temperature. Now let's just put the things here. Let's say this is initial, this is final. Okay, so this is initial, inversely proportional. As the relation is inversely proportional, so I have to write T initial in the denominator if initial is in numerator. Okay, so let's just write the things. We have Ni upon Nf will be final temperature is 27. We have to put it into Kelvin. Okay, so this will be 300 Kelvin. So 300 and 17 degree is 290, right? So we have Ni by Nf, or we can write as Nf by Ni, right? Which will be 29 by 30. Now why I'm finding this? Look, we have to find Nf minus Ni. And we can write, if I take Ni as common, we'll write Nf by Ni minus 1, right? So we have this. So we just need to find Ni. Let's find Ni. So we'll use again this equation. PV is equals to nRT. So PV equal to N number of moles. So N by Na R T, right? Let's just find Ni. So initial pressure was 10 raised to power 5. Volume was 30 is equals to Ni we have to find, divide by Na 6.022 into 10 raised to power 23 into R 8.3 into temperature was, initial temperature was 290, right? So we'll just solve it. So we'll get Ni. Calculation will be a little bit typical. Otherwise, everything is easy in this chapter, right? So let me just write this down. Divided by 8.3 into 290. Okay. Let me use the calculation really fast. I'm going to use calculator into 30 divided by 8.3 divided by 290. Okay. So this will be 10 raised to the power 28. Okay. So this will be 0.075 into 10 raised to the power 28. We'll just put the values here. We'll just put the values here in this. So we'll have Nf minus Ni will be 0.075 to 10 raised to the power 28. This will be 29 by 30 minus 1. So it will be negative 0.075 divided by 30. So I'm just doing this calculation. It will come out to be minus 0.0025 into 10 raised to power 28. So 1, 2, 3, 3 will cancel. 3, 10 raised to power 3 will cancel. So we'll have 10 raised to power 5, 2.5 into 10 raised to power 25. Okay. So D will be the option. So it's an easy question, right? Let's move on to our next question. Let's move on to our next question. Right. So we have two non-reactive monoatomic ideal gases have their atomic masses in the ratio 2:3. Okay, so we will have m1 by m2 equals to 2 by 3. The ratio of their partial pressure in will be at constant temperature is constant, and p1 by p2 is 4 by 3. And the ratio of the density is so simple. We can just write PV equals to nRT, or we can write PM equals to rho RT. You need to learn these two formulas. Okay? So we'll use this. So P1 M1 T1 rho 1 by P2 M2 rho 2 R T2. So R will get cancelled and T1 T will get cancelled because temperature is constant. So P1 by P2 is 4 by 3, M1 by M2 is 2 by 3, rho 1 by rho 2. So simply it will be rho 1 by rho 2 will be 8 by 9, right? So this is a quite easy question again. Let's move on to 47 question. Okay, perfect. Right. So we have a thermally insulated vessel contains an ideal gas of molecular mass m, specific heats gamma. So ratio of specific heat, we know gamma is as Cp by Cv. Okay, molecular mass is m. It is moving with the speed v, and it's suddenly brought to rest. Assuming no heat is lost in this its temperature is increased. So if it is moving with the speed v, then it must have a kinetic energy which is half m v square. Now m is total mass of the gas, right? So we will not take the mass of the container here. I will just ignore it. Okay. Now, if this is the all the kinetic energy and it is suddenly brought to rest, so temperature will increase, right? So this is like heat, right? Now, insulated vessel contains ideal gas. So volume must be constant. We have to take volume constant, right? Okay, so volume of the container is constant. So the heat at constant volume will be N Cv delta T, right? Perfect. So delta T is we have to find. So Cv we need and M small m we need, and this N is number of moles. So we can just write it as half m. V square will be n, and we can write it as small m upon capital M, the total mass, and upon molecular mass, and Cv. Cv we have to write. Okay, so we should know the formula for Cv in terms of gamma and R. Or we can find it, right? So Cp minus Cv is R. Okay, so we can write Cp simply as gamma Cv. Gamma Cv minus Cv equal to R. So we'll get Cv as R upon gamma minus 1. Right, we'll just put it. So R upon gamma minus 1 into delta T we have to find. So this small m will get cancelled. So simply we'll get V square m gamma minus 1 divided by 2R is equals to delta T. Right. So mv square gamma minus. So this case Kelvin, okay. So this case Kelvin gamma minus 1 upon 2R. So D's option is correct, right? Yes. Perfect. Let's move on to our 20 this was our third question, right? So this was our third question. Let's move on to our fourth question. So this was third, okay? Let's move on to our fourth question. So we have three perfect gases, T1, T2, and T3 are mixed molecular masses of M1, M2, M3 number of molecules is this assuming no the final temperature of the mixture. Okay. Now this question is based on partial pressure, right? So partial pressure of the container will be P1 plus P2 plus P3. Right? So let's write partial pressure of the whole system. It will be N total number of molecules R this is sorry moles. This is total number of moles. R temperature of the system or mixture divided by right divided by it will be volume of the container. Okay, will be P1. So partial pressure of first gas will be yes number of moles of first gas R. It must be at T1 right divided by this is N1 is mole here. Okay, and this is molecule. So don't worry, we'll just change it. So we'll write N dash. Okay, now this. So this will be the volume of the gas of the container will be the VC itself. So it will be VC plus similarly N2 dash RT2 divided by VC plus N3 dash RT3 divided by VC. So VC will get cancelled, R would get cancelled. Now NT we can write total number of molecules which will be N1 plus N2 plus N3 divided by Avogadro number T will be equals to N1 dash we can write N1 by Na T1 plus N2 by Na T2 plus N3 by N3 T3 by Na. Look, Na will get cancelled, so similarly T will be N1 T1 plus N2 T2 plus N3 T3 divided by N1 plus N2 plus N3, right? So this is quite easy question. Which option is correct? B, right? Perfect. Let's move on to our fifth question. Let's move on to our fifth question. Yes. So the ideal gas behaves like an okay, the real gas behaves like an ideal gas if its pressure and temperature. Okay, perfect. So we know what was ideal gas. So there was some assumption for ideal gas. One was intermolecular intermolecular forces must be zero, negligible, okay, and the volume of each gas particle should be nearly zero. If how it will be zero, right? How it will be zero if the volume of container is very large, right? And if volume of container is very large, how will it happen if the pressure is low? Okay, and the second thing will happen with the pressure low will be the molecules will be really far apart. And why we need molecules to be really far apart? So that their intermolecular forces will decrease, right? Will minimize. And how will it happen? If you increase the temperature so much that they almost have the kinetic energy only and their potential energy or their intermolecular forces is negligible. Like understand this, if we say the temperature is so high that the molecules have kinetic energy of 1000 joule and their intermolecular forces, if they have intermolecular forces, then they have potential energy and it will be 0.1 joule. So we can clearly say the total energy is almost 1000 joule, right? So they will have zero intermolecular forces or they will have almost zero potential energy, right? So what option will it be? So temperature will be very high Temperature will be very high and pressure will be low. So D option is correct. Okay. Perfect. Next, move on to our sixth question. At what temp at what temperature RMS value of hydrogen molecule is equals to? Okay, so this is quite easy. So we'll just write for the hydrogen. It will be root T of hydrogen divided by molecular mass of hydrogen is 2 will be equals to root T of oxygen. So it will be 273 plus 47. We will be having 320. So we'll just write 320 divided by molecular mass of oxygen. So it will be 32, right? So if you square them, so TH by 2 equals to 320 by 32. So we'll have 10. So TH will be 20 Kelvin. Okay. So quite low temperature, but perfect. So 20 Kelvin. It will be D option, right? 50 D. Okay. Now let's move on to our 51 question. It is saying cooking gas container are kept in a lorry moving with uniform speed. Okay, so this cooking gas is on a container. Okay, so this is our this is a container and we have a gas and it is moving with the speed v. Okay, the temperature of gas molecule inside will. Okay, look, if it is moving with a constant velocity v, then the energy, total energy of system is constant, right? We are not giving any energy. It is already moving. Okay, it is not saying that it was at rest then it start to move. Okay, so this was not the case. It is already moving, right? So there is no energy we are giving, so it will remain same. So temperature and everything will be remain same. Okay, it was a tricky. Let's move on to our 52 question, which is this was sixth, this was seventh, this was eighth. Okay, let's move on to our eighth question. An ideal gas initially at temperature T, right? The volume V, the volume is increased by delta V due to increase in temperature delta T. The pressure is constant. So if pressure is constant, the volume is like KT. Okay, K is some constant. Temperature, you have to draw this graph or system. Okay, so let's draw the graph. So, so we have, if I partial differentiate it, we'll get delta V is equals to K delta T, right? So this is our first equation, or simply I can write it as, if you differentiate it like this, so we will have, okay, let's partial differentiate. So del V will be K delta T, and if you divide them, so we'll have delta V by V will be delta T by T. Okay, right? This is what we have done in unit and dimension also. Okay, so delta will be, so delta V by V into delta T. So delta will be, delta V by V is delta T by T into delta T. Delta T will get cancelled, so it is simply 1 by T. Okay, so this is a y axis, and on x axis we have T. So simple equation will be y is equals to T is x, so it will be 1 by x. So this is our equation. It is rectangular hyperbola. So these two option is incorrect. Okay. So C will be the option. Okay, quite easy question, right? Okay, perfect. Let's move on to our ninth question. So what we have here is a vessel contain 1 mole of O2 and T at a temperature T. The pressure of gas is P. An identical vessel containing 1 mole of helium at a temperature 2T has a pressure. Okay, so this is quite easy. So we'll just use PV equals to nRT. So we have P1 V1 upon P2 V2 will be N1 R T1 upon N2 R T2. Okay, now you must be saying that why you are using this. So look, If nothing is given, then we can consider it as an ideal gas. Okay. So if O2 is not ideal gas, then this is not ideal gas. So the relation will be the same, right? So our life will be easy when we consider it as ideal gas. But be careful. Some question it might not be. Hence, we'll use some different approach. Okay. So here it is just the comparison. Okay. So I'm using it. Perfect. So the pressure of gas. So for O2, we'll write P. The volume of the container is V. Mole is M. R. And the temperature was T. Divided by. For the helium gas, the unidentical vessel containing 1 mole of helium. So mole is one, right? So we write one. R is simple. Temperature is 2T. The same volume V and pressure is P2 we have to find. So it will be, so P by P2 will be by 2. So we will have simply P2 equal to 2P. Right? So this is the this one of it would an ideal gas of temperature is increased from this to this if at this root mean square is this. So we know velocity is proportional to root T, right? So if temperature is increased 4 times, so velocity will increase 2 times, right? So it was initially V, right? Now it will be 2V. Okay. So you don't even have to solve them. Let's move on to our 11th question. Three closed vessels A, B, C are at temperature T. Contain gases which obey Maxwellian distribution of velocity. Okay, so it was like this. NFRT divided by 2, right? The vessel A contains only O2. Okay, so the three vessel. So this is A. Only contains O2. We have B vessel. Only contains N2. And we have a C third vessel. Mixture of equal quantity. So it will be O2 plus N2. And they are equal in quantity. If the average speed of O2 molecules in vessel A is so so the average speed of the molecules was what was the formula? So it will be root 8 RT by pi m. M is the molecular mass, R and T is the temperature. So from this we have found this, right? We also have found RMS and whatever and so many things, right? Okay, so the average speed of O2 molecules in the vessel is V1. So here it is V1 and in the B2 it will be V2. So the average speed of O2 molecules in vessel 3. So look, the temperature in all the three is TTT, right? So even though we have an O2 and N2, the velocity depends only on the temperature and the molecular mass. And if we are talking about O2 molecules, so M of O2 molecule will be same as A, right? Because in A there was O2. So the velocity and the temperature in all three will be T. So simply the average velocity of container C P V1, which is the velocity of O2. It's quite easy question, right? Let's move on to our 56. So we have monoatomic gas of gamma this is mixed with diatomic gas of gamma this. Okay, so gamma of mixture we have to find. So for gamma of mixture, we need to find Cp of mixture upon Cv of mixture, right? How will we find it? So we know the Cp of mixture will be N1 Cp1 plus N2 Cp2 plus N3 Cp3 to so on divided by N1 plus N2 plus N3 and so on divided by N1 C1 plus N2 Cv2 plus N3 Cv3 so on divided by N1 plus N2 plus N3. So on. This will get cancelled, so we'll just find this. Now, for the monoatomic, Cp is 5, right? 5 R by 2. So Cp1 is what? 5 R by 2, and Cv1 will be 3 R by 2. Okay? From the gamma, we can find that. And for Cp2, for second case diatomic, it will be 7R by 2, and Cv2 will be 5R by 2. Let's just put all those values here. And now number of moles are same. So we'll just write Cp1 5R by 2 plus Cp2 7R by 2 divided by 3R by 2 plus 5R by 2. Right? We know this formula for the mixture we need to find like this. Okay. So 2 will just cancel. So it will be 12R divided by 8R. So we have 3 by 2. So it will be 1.5. So which option is correct? B, right? Okay, perfect. So this was our 12th. Let's move on to our 13th question. So 13th question. At a room temperature, the RMS velocity is this gas is. So we can find this, right? We just need to find the molecular formula. So it will be 1930 be root. It was RMS. So 3 R. It will can write 25 by 3 T. Temperature at room temperature was 300 Kelvin divided by molecular mass, right? So we find molecular. So that's it. That is easy, right? So we will get cancel 100. So if you square it, so we'll have m 2500 into 3 divided by 1930 to the whole square. Okay. So if I use the calculation really fast, we'll have into 3 divided by 1930 divided by 1930. So we will have 0.002 grams, right? So molar mass is gram per mole. Okay, so it will be per mole. Okay, so okay, in kg, it was in kg because all were in SI unit. So this was in kg. So we will have 2 gram per mole, and it was hydrogen. Okay, let's move on to 14th question. So these are quite easy, right? They are like work, power, energy. Okay, perfect. So we have these question. A closed container. Okay, let me expand this so that okay, perfect. A closed container or volume this contain a mixture of neon and argon gases at a temperature this and pressure this. Okay. The total mass of the mixture is 28 gram. The molar mass is this, and the masses of individual gases of the container. Okay. And then, so this is a total pressure. So total pressure is 1 into 10 raised to power 5. And the temperature is 300, right? So the molar mass is this, when the masses of individual. So total mass is given. So let's just write the equation first for the partial pressure. We'll have total pressure is P1 plus P2, partial pressure of both phases. So P will be, I will write it as nRT divided by total pressure. Okay. So first will be N1 RT1. So temperature will be the same, right? Upon, okay, volume. So it will be V. So V plus N2 R T2. So temperature will be the same, right? Upon volume. So these will get cancelled. So we will have simple N equals to N1 plus N2. Number of moles of 1 plus number of moles of 2. Right? Okay, so we have volume and we have temperature. Okay, we have volume, right? We have the volume. So how can we solve it? So let's just say the mixture, the molar mass of the mixture is M equivalent. Okay, so we can write it as the total mass upon M equivalent will be equal to M1 upon M1 plus M2 upon capital M, right? So M total is 28 upon M equivalent, and this is M1 upon capital M1 was, so the first gas will take neon 20 plus M2 upon 40, right? So this is our first equation. Now the second equation will be simply M1 plus M2 will be 28. So this is our second equation. We need to find M equivalent. So let's just use PV equal to nRT, PV equal to nRT, right? So P pressure was 10 raised to power 5, volume was 0.02, and will be M total, M28 divided by M equivalent. R will have to take 8.314, right? Into temperature. So temperature 27 degrees Celsius, so it will be 300 Kelvin. Okay. So we'll get M equivalent from here. So we'll just write it as 28 into 8.314 into 300 divided by 10 raised to the power 5 into 0.02. So I'll use the calculator really fast. 28 into 8.314 into 300 divided by 0.02. So we will have, so we'll have almost 3.5 into 10 raised to power 6. 10 raised to power 5. So we will have 10 raised to power 1. So it will be 35. Okay. So just use the equation here. If I put in M2 28 minus M1, so it will be M1 plus 28 minus M1 upon 40, 20, 28 divided by 35, right? So what will get? So I will take 1 by 20 as common, so 28 by 35 will be equal to 1 by 20, and this will be 2m1 plus 28 minus m1 upon 2. Right? This was 2. Okay, perfect. So we will have simply 28 into, this is 4, this is 7, right? And this is 4. So it will be 16 into 2. So 16 into 2 will be 32, will be equal to 2 m1 minus m1. So it will be m1 plus 28. So we will have m1 will be 4 grams and m2 will be 24 grams. Okay, so quite easy question, but a little bit of calculation is involved. So let's move on to our 15th question. So we have Two glass bulbs of equal volume, two glass bulbs of equal volume are connected by narrow tube, are filled with the gas at 0 degrees Celsius and pressure is this. Okay, one bulb is then placed in a, so we have two bulbs. So situation is like this. Let me just insert some space here. Okay, so this is our 15th question. So we have two bulbs like this, right? And they have a gas at zero. So here it's some gas, here it is some gas, and almost narrow tube. So we'll have gas like this. So both have pressure P naught and temperature 0 degrees Celsius. One of the bulb then placed in melting ice. So if this is placed in melting ice, so has a temperature 0 degrees Celsius, so no change here. Where was, yeah, the other was placed in a bath maintained at 62 degrees Celsius. So now this contained in temperature 72 degrees Celsius. So temperature is no more here. So pressure will be not, pressure will be not be P naught, so it will be P1, and the pressure may be here at P2. Okay. What is the new value of pressure inside the valve? Okay, so look, the pressure starts to change, but eventually what happens is that the gases will start to move here. As the temperature increases, pressure will be more here. So it will start to move here, and eventually what will happen? The pressure of both will remain same. Okay, so we'll have to use this. So let's just use as a PA, let's say it is PB. So PA equals to PB. Okay, now look, if it has a mass m and it will also have a mass m because the volume is same, temperature was same initially. So let's just say x mass has moved from here, so it will get the x mass, right? So we will write yes, pressure, number of moles into RT upon volume, right? So it will be NA RTA upon P V will be equals to NBRTB. So we'll get cancelled, R will get cancelled. So Na will be m minus x upon capital M. The gas was same, into temperature at A is 72 degrees Celsius. 72 or 62, I think it was 62, right? So we will have 335, right? 335 Kelvin will be equals to NB. NB will be M plus X by M. Molar mass will be same. Temperature will be 0, so it will be 273. So M will get cancelled. What we have to find the new value of pressure inside. Okay, so first we'll just find the X here. So it will have 335 M minus 335 X will be equal to 273 M plus 273 X. So we'll get X in terms of M, small m, right? So what we'll get? 335 minus 273. 335 minus 273, it will be simply 62. So 62 M will be equal to 335 plus 273. It will be 608, right? 608 X. So we'll have X as 62 M upon 60. So this much of mass has left from 1 to 2. Now we'll just find the pressure. So initial pressure was, it was mRT upon capital M into V. Yes. Now the new pressure will be for any one of the case you can find. So we'll just find the for the A. So A will be M minus X, right? Into R into temperature is 335. So let's just find for the B, because what will happen, the temperature term will get cancelled. So it was 0 degree Celsius, right? So 270. Just let me write those values here. So let's just write the values. P naught will be N M R into 273 divided by capital M into volume, and this will be equal to PB. It will be M plus X. So it will be M plus X R into 273 divided by M and V. So if I divide RMV will get cancelled, 273 will get cancelled. So P naught was 76 mmHg, right? 76 76 centimeter. 76 centimeter upon PB will be M and M plus X. So M plus X will be M plus 62608. So M will also get cancelled. So 76 centimeter into PB, 608 upon, it will be 670, right? So we will have simply PB as 670. I'll use the calculator really fast, into 76 divided by 608. So we'll get 83.75 centimeter of Hg. Okay, so it was quite easy question. Let's move on to our 69. Let me insert some space here. Okay, so let's move on to our 16th question, shall we? Okay, let's just put this one. Okay, right. So let's move on to our, it was 16th, right? 16th question. So we have a jar contains a gas and a few drops of water at a temperature T. So we have a jar, and there is a few drops of water, and we have gas here. It's at temperature T, and maybe pressure is 830 mm Hg. Okay. Now the temperature of jar is reduced by 1 degree Celsius. So new temperature will be T minus 1%. So it will be 99 T by 100, right? The saturated water to temperature. So here P naught of water was 20 mm. And what will happen now? Okay, so as the temperature increases, partial pressure will decrease. So it's not 20, it must be 30. So this is 30 mm. Now, as the temperature decreases, so P dash of water will become 25 mm, right? So we have to find the new pressure of this jar. So look, the temperature decreases, the overall pressure should also decrease. So let me write the equation for the partial pressure, right? So what it was, so it was a P naught of container, P naught of water plus P naught of, yes, it will be equal to P naught of gas. Now for the final pressure P dash of container will be equal to P naught of uh, P dash, it will be P dash of water, the new partial pressure of water, right? So new partial pressure of water plus new partial pressure of some gas, whatever it was, right? Okay. So what do we write here? So it was 830 initially, and partial pressure of water was 30 plus partial pressure of gas. So partial pressure of gas becomes 800. Okay. Now let's find the new partial pressure of the gas and then just we'll add and we'll get this. So we know PV equals to nRT. So this P naught G will be equal to nRT divided by V. Now this will become volume is same, it is V, N is same, R is same, but temperature will become 99 by 100 T. So P dash G will be nRT by V into 99 by 100. And nRT by 100 was 800 into 99 by 100. So we will simply have 99 into 8. It will be 792. So new pressure will be, the partial pressure of water was 25 plus, and it becomes 792. So we will have 7 870 mm. Okay, so quite easy question again. Let's move on to our 17th question. So these are just true false questions. So we write it here. The RMS of oxygen value at a certain temperature is T is V. Okay. If the temperature is doubled, oxygen gas dissociate into atomic oxygen. Okay. So initially molecular mass was let's say 32. Okay. Now the new molecular mass will become they are dissociated, so it will become 16. Okay. And temperature is double. So initial temperature was T. Now temperature is 2T. Now we will know proportional to T by M. So if this becomes half and this becomes double, right? So velocity will be root over 4 times, which is velocity must become 2 times. Remains unchanged, so wrong. So this is false. Okay. 18th question. Two different gases at same temperature have equal root mean square velocity. So look, different gases. So molar mass will be different. So they will not have same. So this is also false. Okay. For the 19th question, the volume versus T graph of a certain amount of gas at two pressure P1 and P2 are shown. It follows P1 is greater than P2. So if we have to find the pressure, so we'll know P is V equals to nRT. Okay. So we'll just take volume as constant for both. So P will directly becomes proportional to temperature. So how we'll take V constant? We'll just make a horizontal line like this. So for P1, this is T1 and this is T2. Clearly, T2 is more than T1. So P2 will be more than P1. Right? Simple. So it's again false. All are false. Let me just check for a second. This false, false, false. Okay, we are solving correctly. Right? So next question, if you see a true false in JEE Advanced from KTG, you just mark it as false. I'm joking, don't do that. Let's solve the 20th question. The root mean square speed of molecules of different ideal gases maintained at same temperature are same. What? It's same question. The root. Different ideal gas maintenance. Oh, it's again false. Okay, 1981 and 1982. Repeated questions. Wow. Let's move on to our 21st question, and we need a little bit of space here. Okay, so what is that? A ring-shaped tube contains two ideal gas with equal masses M1 and M2. Okay, so here it is M2, and here, so let me, this is M2. Okay, perfect. Okay, M1 and M2. The gases are separated by a fixed partition and another movable stopper S, which can freely move like this. The angle is alpha. Okay, so look, if they have equal mass, then what will happen? The pressure here initial will be P1 and P2. Now finally, what will happen? This stopper start to move and the pressure eventually will become same. So pressure here and pressure here should be same. Now we do not need a gravity kind of thing here. So we'll just equate the partial pressure of these two. So look, P1 must be equals to P2. So P1 will be what? It will be N R, and the temperature is same, volume will be different, V dash. So N1 by V1. Okay. N1 R T by V1. And P2 will be N2 R T by V2. Right. Okay, perfect. Look, this area will be the same. This area will be like this, right? So it will be cylindrical, more of a cylindrical inside, right? Simply we can say the volume is proportional to alpha. Okay. Now for M2, volume will be alpha into K. So look, volume is directly proportional to angle. Okay. So for V2, so V2 will be alpha into K, right? So for V2 will be alpha into K, and for V1 it will be, this whole angle is 360, so it will be 2 pi minus alpha. Okay, so let's just equate them. If they are equal, then N1 RT by V1. V1 is 2 pi. So let's just put values for all, right? Directly. Okay, so they are equal. So N1 will be mass m upon 32. So m upon 32 into r, temperature is same, and volume V1 will be 2 pi minus alpha into K. This is some constant K. V2 will be m upon 28 into r into T divided by V2. V2 will be alpha K. So K will get cancelled. M will get cancelled because they had same mass. So we'll simply have, if you cross multiply, okay, so this will be simply 32 into 2, 64 pi minus 32 alpha will be equal to 28 alpha. So we will have 64 pi will be equal to, this will be 60 alpha, right? 3 to 5. Okay, perfect. So we will have alpha 64. In degrees we have to find, so pi is 180 degree divided by 60. So this will be 3. We will have 192 degrees. Okay, quite easy question. Let's move on to our 22nd. We need a little bit of space here. 22nd. Okay, now what is given in this question? A thermally isolated cylindrical closed vessel of height 8 meter is kept vertically. It is divided into two parts by the diathermy, perfect thermal conduction. So heat will get exchanged. There's a partition is frictionless initially at a 4 meter. So this is 4. and this is also 4. Okay, the top of now each two parts of the vessel contain 0.1 mole of ideal gas. So N is same in both. The partition is now released from and moves the gas on part. Equilibrium is reached. Okay, so this is simple. Look, this partition has some mass. So it will happen if you release it, it will start to go down. Why? Because it has mg. Now what will happen? The pressure inside will become here, it will become P2 and here will become P1. So what will happen if I make a free body diagram? If I make a free body diagram, so P1A will act here and P2A will act in the downward and mg will act downward. So P1A will be balancing these two, right? So P1A will be equal to P2A plus mg, right? Okay, so let's just say it moves so by some distance, right? It moves by some distance, I don't know. Let's just say this, let's just say it moves by distance x because we have to find the x. What we have to find first, let's see the distance of the partition from the top will be. So this we have to find. So let's just take this as x. Okay, so let me make another diagram. So we have this container and this is our partition, and let's say this is x, so this will be 8 minus x. So P1 will be according to this and P2 will be according to this. So they do P2, so let's just write it. P1 will be an R, temperature. Okay, so what will happen, temperature will also be same because this is perfectly thermal conductor, so temperature will be same. So we'll write it as temperature T, right, divided by volume. For volume, we can write this as area A into 8 minus x. So A into 8 minus x, and this is our area A. Now P2 will be nRT upon area A into x into area A plus m. M mass of partition, it will be 8.3 into G is 10. Okay, G is 10. So A will get cancelled and we have nRT 1 upon 8 minus x minus 1 upon x will be equal to 8.3 into 10. Now the temperature will be, each of two parts vessel will contain at a temperature 300 Kelvin. The partition is removed. So what will happen if it start to go down? Temperature will change, but eventually what will happen? Eventually, what will happen? The temperature of both the container will become same. Why? Look, there is no heat is exchanging from outside. So you can use a first law of thermodynamics. So Q was delta U plus W, right? So outside, there is no heat given from outside. So work done will be equals to delta U. Work done will be equal to delta U, right? And look, for on this system, there is no work done. So delta U of the system should be 0. If delta U is 0, delta T should be 0. So initial temperature must be equal to final temperature. So we'll just write N was 0.1. R have to take 8.3. Temperature is 300 and you will take the LCM. So it will be X. This will be minus 8 plus X. So 2X minus 8 upon X into 8 minus X. It will be 8.3 into 10. So 10, 8.3. So one decimal will also get cancelled. So this is simply 3. If you cross multiply, we'll get 8x minus x square. And this will be 6x minus 24. Okay. So we just have to solve this quadratic equation. X square minus 2x minus 24 equals to 0. Right? So we'll use minus b plus minus under root b square 4 minus 4ac. So 24 into 4, right? So it will be 96 divided by 2. So it's easy, right? 2 plus minus under root 100 by 2. So we'll have 2 plus, we have to take 2. Okay, everything is same, right? Everything is, there's nothing wrong. Okay, this is 10 divided by 2, right? So yeah, 10, not 100. Okay, so it will be 6. So x will become 6. So 6 will be the answer. Okay, so quite easy question. But this concept was very important, right? Work done on the system, 0. So temperature will of the system will remain the same. Okay. Let's move on to our 23 question, 23rd question. 23rd, then we have to. Okay, so this is actually very hard question. Okay, but quite interesting. So there are a lot of solutions online. Most of them are incorrect. Trust me. Let's solve. So we have this cylindrical vessel. Okay, what is happening is, let me just, you can read it yourself. Pause it, pause this video and read it. Let me just explain. So look, from here, gas is coming in this side, okay, at a density rho, pressure PA and temperature TA. This furnace is giving heat to this gas and the temperature is raised. So TA to 360. Okay, just let me make the diagram here, right? Okay, so we have gas here, whose density is 1.2, temperature is 300 Kelvin, and pressure is PA. Right? We don't know PA. Okay, we don't. Perfect. Now it is going here. What is happening? This gas is heated. The temperature is increased here, but what happens is pressure remains same. Okay, density will be changing because temperature is changing. So temperature will become 360 Kelvin. Okay. Now what happened is this is raised like this. So density will be same. Pressure will be pressure will start to change. So here let's say pressure is P naught, but density is same, right? And what happens to the temperature? Temperature will be same. Because the hot air with the density rho rises up vertically of the diameter this and exits the chimney. Shift. Okay. Assume the air ideal, neglect the variation of rho and T inside the chimney and the furnace. So for here, the temperature is same. It's T will be 300. Okay. And density will also remain same. Density will also remain same. Okay. Because it is same. So density will be same. Right. But pressure will be different. So here it is PA and here it is P naught. Okay. What is happening is we are giving it heat. So heat is given. Okay. Now find the okay, we have to take streamline uh, the airflow to be streamlined, and we have to find the mass flow rate. Like here, what will be dm by dt? Okay. Now to solve this, let me mark some point, some you know points or some region. Okay, to be precise. So this is our first region. Here, here, and here. So this is first region, this is second, this is third, this is our fourth region, this is fifth. So many region will not use, understand this, look, what is happening is as the air goes inside, it gets temperature, it gets heated here, and then it rises. So here, the temperature, the heat we are keeping. So from 1 to 2 or 1 to 3, the temperature, the energy is not constant. So we are providing the energy. Okay. So look, we have to find the velocity. So we have to use Bernoulli's equation. Yeah, Bernoulli's theorem, right? So if you want to use Bernoulli's for 1 to 3 or 1 to 2 or 1 to 3 to be precise, we cannot use it. But when the air is here and it gets the heat, right? So from 3 to 5 we can use the Bernoulli because there is no heat exchanging from here. So 3 to 5 as it start to raise, right? So I'm giving the heat till this region, let's say, right? So here it will get the heat, but after that there is no heat given to it. So to use Bernoulli, we have to use for region 3 to 5, 3 and 5. Okay. Now, this is the first. Second, we have to use this information. The airflow is streamline. So streamline was what? So it was uh, the mass entering and exiting was same. So we have to use this A1 V1 is equals to A2 V2, right? But to use this, to use this, their density should remain constant, right? Air density. So from 1 to 2, 1 to 3, we cannot use this. So we have to use from 3 to 5 again. So this again is used for 3 and 5. Okay. So let's just start the situation. So now you will say, sir, what is the use of this 1 and 2? Okay. So we for 1 and 2 or 1 and 3, to be precise, 1 and 2, will use the rate of flow of mass. Rate of flow of mass. What is happening is, look, the mass entering this furnace. So let's say it is M E N T. So this is mass entering the furnace must be equal to mass out or mass exiting the furnace, right? With this information, so we'll write simply here. I will write it here. I'll write it here. Okay. So mass entering the furnace will be equals to mass exiting. Okay, mass, right? So with this information we can find the density. So let's just start to solve it. Okay, let's use the third information for the uh, so what is saying third information, what is this saying? Mass entering. So how much is the mass entering? So density is rho a into volume. So it is entering from this, right? And this has a diameter d. So we'll just write pi d by 2 to the whole square, right? Into into uh let's just say uh or can we use right, simple PV equals to nRT. Let's just use because we have temperature and all those things, right? So we'll use that. So look, so we have an equation called Pm equals to rho RT. So molar mass is same. Uh, we don't know the pressure, right? We don't know the pressure. We have the density, we have R and we have T. Okay. So if we use this equation, we need 2 points in our situation where we can use this. Okay. Uh, so can we take 1 and 3 because the pressure is same here, right? So for this, to find the rate of flow, to find the rate of flow, we will simply use the pressure, the ideal gas equation at 1 and 3, right? So we'll just write it as P1 M1 divided by P2 M2 will be equal to rho 1 R T1. So we'll taking 3, right? So let's just say 3 upon rho 3 R T3. Okay. Now the pressure is same. Pressure is same at 1 and 3. Molar mass will be the same. The gas is same, right? Okay. Now R will cancel. Now density will be, so this is 1 by 1. So density at A will be 1.2. The temperature at A will be 300. Now the density at 3 is rho into the temperature at 3 is 360. So we'll have density as 12 into 330 divided by, because 1 will cancel, divided by 360. So 1 will cancel. This is 12. This is 1. So density will come out to be 1 kg per meter cube. Okay. So first part of the information we get. Now let's use these. Okay. First let's use this. So we have A1. So where we are using it at 3 and 5. So A3, A at 3 will be what? A at 3 will be pi capital D by 2 to the whole square, and let's just say velocity here is v, okay, and here it is v naught. Are you getting me? So here velocity is v and here velocity is v naught. So this is v, okay, at 1, and this will be at 3. This is at 3. This is at 5. Okay. Now at 5 it will be pi d by 2 to the whole square into velocity at v5 is v naught. Okay. So this is our first equation. Now let's use the Bernoulli's. Let's use the Bernoulli's. So look, where we have to use the Bernoulli at 3 and 5. Okay, at 3 and 5. So after it gets the heat, it start to rise. Okay, so at 3 the pressure is simply Pa plus. If this is our base, then this is our height and it is given, it's 9. Okay, 9 meter. So if this is base, rho gh will be 0, rho g into 0 plus half rho v square. Where is v? Here. Its pressure is P naught plus half rho v naught square plus density is rho. Density is rho g and at height 9. Okay. Are you getting me? Okay, perfect. Now we have to understand the relation between P naught and PA. Okay, now we have to understand the relation between P naught and PA. So look, uh, this. So now we need to understand about this P naught. Okay, so this P naught is actually the pressure of atmosphere. Okay, and if it is a pressure of atmosphere, so let me write this P naught is the pressure of atmosphere. Okay, right. So if this is a pressure of atmosphere at here, at this point, so we have to consider the density of the atmosphere as rho a, right? Because the density of atmosphere was rho a. Okay. Now this P naught pressure which is at here, so if it at this point the pressure is PA, so this is P naught pressure, right? Okay, so this was rho density, it was written mistakenly. Yes. So we have to consider this length, which is actually 10 meter. Now, in the IIT's solution, they have taken 9 meter. Okay, so they have taken this 9 meter, which is wrong. Which is the This question is actually from the MIT. Okay, so they have just copied paste it from there. So, but we'll take 10 meter to find the exact answer. So PA, this will be 0 plus half rho V square will be put from here. Okay. Now, as D is less than capital D, much less than capital D. So D, look, okay, so we'll find V will be, so this pi 4 will get cancelled. So we will be D square by D to the power 4 into V naught. So we'll just put it here. So it will be square. So this will be D power 4 upon capital D power 4 V square, V naught square. And P naught will be P at A minus density of air into G into H. We'll have to take it as 10. Okay, this is P naught. This is half rho V square. So this is half rho V naught square plus rho G 10. Now this PA will get cancelled, and as D is less than D, so we'll ignore this. This will be 0. So this 0 equal to, we'll get rho A. It is 1.2 into 10 into 10 plus half rho is 1 V naught square plus rho will be 1 into 10 into 10 100. This is minus, so we will get half V naught square will be 30, and we will get V naught as root 60. Look, again I'm saying, according to IIT this should be 6, but that is a wrong solution. Okay, now if we get V naught, we have to find dm by dt. So dm by dt will be d by dt rho a into x, and we know the this rho a is constant and dx by dt is this. This is actually v naught. So rho density. Now the smoke is getting out, so density will be rho. The density of smoke or the heated air is 1. Area will be pi d square by 4 into v naught as a root 60. So it will be 3.14 will take into d square. So d was 0.1, right? Yes, so 0.1. So it will be 0.1 to the whole square divided by 4 into root 60. Okay, so I'll use the calculator. 3.14 into 0.1 into 0.1 divided by 4, right, into root 60. So this will turn out to be, 0.06 kg per second. Okay, right? So like we can find it according to gram per second. So it will be into 1000. So it will be 60 gram per second approx. Okay. But if you have written here 6, so we'll be getting 3.14 into 0.1 to 0.1 into 6 and divided by 4. So we will be getting 47.1, but that was the wrong answer. So this was correct. Okay, this is our answer. Perfect. Now, when the chimney is closed using a cap at the top, the pressure difference delta P develops between the top and the bottom of the pressure. If the changes in temperature and density of the hot air due to superficial effect are negligible, find the value of delta P. So this is quite easy. So for this question, what it will be? Now, look, the pressure here will be PA plus rho of smoke G into small h. eh? And pressure will be, so this is A, this is P. So pressure here will be PA plus density of air G into 10. Okay, so delta P will be PA minus PB. So it will be rho GH minus rho AG into 10. So rho will be rho was 1 into 10 into 10 minus rho naught. It was 1.2 into 10 into 10. So it will turn out to be 100 minus 120. So it will be 20. Okay, Newton per meter square. So minus saying that uh, PB will be more. Okay, PB will be more. But if you solve it again using the solution from JEE, you will simply write it as according to JEE. So this will be this should be 9, right? So if you put it here 9, then 100 minus so this will be 9, right? So it is uh 9 will come here, right? So if I solve it using the J solution, so this will be 1 into 10 into 9. So this will be 9 minus, and the pressure. Okay, so I've done some mistake, right? Okay. So this small h is actually 9, right? That is the mistake I have done here. So this is 9. Okay. So 1 G, this is 9 minus 1.2, 10 into 10. So we will get 90 minus 120. So it will be 30. So my answer will be 30 Newton per meter square. But according to IIT, it will be, so here it will be 1 into 1 or 10 into, this will be 9 minus rho naught, it will be 1.2 into 10 into, this will be 9. They have taken it as a 9. So this is 90 minus 108. So it will be minus 80. This will be, of course, wrong. Okay. So these are controversial, but the solution should be like this. Now let's move on to our last question, 25. During an experiment, ideal gas is found to obey an additional law. This will be Vp square equals to constant. Okay, and we will have PV equals to nRT. The gas initial temperature T, volume V, and it expands to become 2V. So the temperature will be, okay, perfect. So initially the temperature was PV divided by nR. Okay, now the volume becomes 2V. If volume becomes 2V, then we will have 2V P dash square equals to V to P, because P square, right? So this will get cancelled. So P dash will be P by root 2. So this will be the new pressure. This is the new volume. So we'll simply write it as P dash will be P dash V dash upon NR, and P dash is P by root 2. P dash is 2V divided by NR. PV by NR was T. So new temperature will be T root 2. Okay, this was an easy question. So it will be T root 2. Okay, so this marks an end to our discussion. Thank you. Bye bye.